Hey folks, my name's Tim Swena. I'm a staff software engineer at Google. I lead the BigQuery DataFrames team. And today we're going to have a hands-on workshop where we're going to use BigQuery DataFrames to process some structured and unstructured data using some of the advanced AI technologies that we integrate through BigQuery. So for folks that don't know, BigQuery is Google's analytics product. So it provides scalable analytics via generally SQL, and BigQuery DataFrames provides a Python interface to that. Important thing to know about BigQuery is it scales the compute separately from the storage. So BigQuery provides a scalable storage backend, storing data in a columnar format optimized for analytics. It's kind of analogous to Parquet. And we have a very scalable compute engine that takes advantage of that storage. And so for you folks as potential customers of BigQuery, what that means for you is you pay for what you use. So if you have a very small table, you only pay for the bytes that are stored, but you might use some very complex queries on that table. And so that compute infrastructure can scale up and scale down as needed. And then using that with Python, generally you would interface with BigQuery via SQL. So you might use a library like Pandas GBQ, which my team also helps maintain. So Pandas GBQ, you give it your SQL or you give it your table. It runs that using BigQuery's query engine, and then it gets it back to you to store in your Pandas data frame as quickly as we can. And then from there, you can use your full open source ecosystem because your data is local. Now, there might be some troubles with storing data locally. For one, it means you do have to write SQL in order to work with BigQuery. And that's where BigQuery DataFrames comes in to help push down your Pandas operations to the query engine instead of having to go through that. The other problems you might have are scaling Pandas. So you only have so much memory on a single node. You can only do so much with Pandas before it falls over. So there's lots of scalable data frame libraries that have been built to address that. And BigQuery DataFrames kind of fits within that ecosystem. Another problem might be, your company might have an issue with you downloading a ton of data to your notebook for processing. They might want you to keep that data in BigQuery. So that's where BigQuery DataFrames comes in. So you can write your Pandas-like code, or if you're doing machine learning, scikit-learn-like code, and BigQuery DataFrames will push that down to our SQL engine without you having to write SQL. All the analytics happen much closer to where the data is. You don't have to download it to your notebook. So you can see here, it looks a ton like Pandas. We've implemented over 700 Pandas methods, and continue to add more. Our goal is to be as drop-in compatible with Pandas as we can. There are some trade-offs, which we'll talk about more in the hands-on section. We can also extend with open source or proprietary code using cloud functions. So we provide what's called the remote function annotation, or you can decorate a function with at remote function, and we'll deploy that to the cloud and be able to call that from your Python code, but also SQL code. And we have also implemented some of the visualization methods that Pandas provides, so that we can automatically do the aggregations for you before downloading that to your notebook. On the ML side, it's less of a drop-in replacement here. It's more inspired by scikit-learn, I would say. Although for simpler models like linear regression, it is pretty close to a drop-in replacement. These are built on BigQuery's machine learning API. So we have in BigQuery ML, there is a create model statement, and any code you write in this bigframes.ml package will push down to BigQuery ML. And in some cases, BigQuery ML will integrate with Vertex AI, and we'll use that today as well for some of the more advanced models. So at a high level, we've got BigFrames as your interface to BigQuery, pushing down your pandas and scikit-learn to that query engine. You can expand that ecosystem with custom functions, including third-party packages deployed to Google Cloud using Cloud Functions and exposed to BigQuery via remote functions. And we have access to the latest and greatest LLMs and related models and tools, as well as streaming operations. So it can be part of your data pipeline to push data as it comes in from BigQuery to Bigtable and PubSub. So for the folks here, I'd like you to fill out this pre-survey. It'd be great to learn a little more about why you're here and what you're hoping to learn. And then as well, I recommend using an @Gmail address for the folks attending in person, because then we can add you to a shared project that we're going to use for this demo, and you can follow along as we go. My teammates, Matthew Chen and Yufeng Guo, are here to help you get on board. So if you have a question or get stuck, raise your hand. But yeah, I'll give you a few minutes to fill that out. And then we have a question. The question is, for that remote functions integration, how much code do you have to write? So if you've used remote functions without the BigQuery DataFrames package, you'll see in the docs, there's a very specific specification for the web server you have to create, and how to parse the JSON and return a very specifically formatted result. We take care of that in the BigQuery DataFrames package. So we abstracted away in that it looks just like a Python function that you would use and, for example, apply in Pandas. You just annotate it, give us a little type information, and we'll create that web server for you, deploy it to Cloud Functions, and set that up so that BigQuery can access it. So, we have made that interface a lot simpler. And then, for the folks attending in person, we have, you should be receiving an email that looks like this. This is an invite to our shared project. So if you go ahead and click that link, it should add you. All right. And if you'd like to follow along on your own, I recommend going to this bit.ly link. So it's bit.ly/bigframes-kmeans-codelab. So that gives you a bit of a hint as to what's to come. We're going to use the k-means clustering algorithm as part of our workshop today. It gives you some instructions on how to set up a Google Cloud project. If you're running this at home, go ahead and follow those steps. You can use the free trial if you haven't used that already. Some of this might be compatible with the BigQuery sandbox, but other steps like the machine learning will need a billing account. So that link should take you to a page that looks like this. This is our code labs, and it can see we've got the steps on the side there, and we're going to go through these together, and I'll demo as well, but would love for you to follow along as we go. Yeah, we're still getting some folks connected to our shared project, so working through that. Thanks for your patience. All right, yeah, so these are the steps to create that project. For the folks in person, you should end up on a project that looks like this. We're using this shared PyData NYC project that we'll delete at the end of the conference. But yeah, you'll end up on this Google Cloud page. There's a ton of products for Google Cloud. We're going to be using BigQuery today. Easiest way to get connected to that is the search box, and then type in BigQuery, all one word, and then select the one that's BigQuery Data Warehouse/Analytics. So there's been tons of terms over the years in terms of what do you call these analytics-driven databases. I've heard data warehouse, I've heard data lake, I've heard data swamp. So the marketing tends to change, but with the capabilities, we're calling it a data warehouse today. And you should see this welcome screen. If you do, go ahead and click that Python notebook. If not, find that little triangle, and we'll click that and create a Python notebook that way. Since this is a project I've set up before, everything should be good to go. If not, if it's a new project, it'll have a pop-up with some APIs to enable. We don't need these templates, so we'll just close those. And we'll click Connect. So the first time you click Connect, it's going to create a virtual machine in the background to power this notebook. That might take a few minutes, but in the meantime, we can click the Code button, and that'll let us enter some code even while we wait for the notebook VM behind the scenes to get running. So this is a Python notebook in BigQuery Studio, but it's powered by Google Colab. So it's an enterprise version of Google Colab. Both Colab and BigQuery Studio have the BigFrames package pre-installed, but we can install it manually with this pip install command as well. So generally the version on the Colab image is a few weeks behind what we have on pip. So by doing this pip command, it makes sure we're running the very latest. This command will work with, or our workshop will work with the current version on Colab. So very much an optional step, but feel free to do it to make sure you've got all the latest fixes and performance improvements. So we are connected to the machine now. So that little pop up was showing the size of the VM that's powering this. And so we know that we can use BigFrames because we've installed it. So to get started using it, we'll need to import it. So generally for using pandas, folks do import pandas as PD. Here we're using, the BigQuery DataFrames flavor of pandas. So I'm calling it BPD to disambiguate because we do end up using both BigQuery DataFrames and pandas in the same notebook quite a lot. So we use the B to disambiguate that. And then an important part about this workshop is we're using partial ordering mode. That's going to make some of our queries more efficient, but it's also going to mean some features that would be pandas compatible aren't always going to work, at least not right away, without adding an explicit ordering or an explicit index. So without setting this, what BigQuery DataFrames tries to do is assign a deterministic ordering for every row in the table. It does that via some sophisticated stuff, mostly a hash, plus some stuff to disambiguate if there's duplicate rows. But you can imagine that could get a little expensive compared to writing SQL by hand. So using ordering mode equals partial is going to make sure the SQL we generate looks a bit closer to what you would expect if you're writing SQL for BigQuery. We've got some folks who still have trouble connecting to that shared project, so I'm going to pause and help them. So one thing you can try is, I'm not logged into my corporate account, so it took me to a different link. But if you go to console.cloud.google.com, you should be able to select that PyData NYC project that we created for the workshop today. Yeah, so that's console.cloud.google.com. And then, if you do /?P equals PyData NYC 2024, that should take you to the shared project as well. Are we back? Okay. Seems like most people are connected. So that link should have taken you to a page that looks like this. In the search bar, type in BigQuery, and we want that data warehouse analytics link. And yeah, you can either click Python Notebook or the triangle and select Python Notebook. We don't need the templates. And connect to create that VM backing the notebook. Or it'll connect to the one you had before if it's not your first time doing it in a while. So is everyone caught up? All right, so we've got our notebook. It's got a connection. We can click the plus code button either in the editor or up on the top left there. And let's start using the BigFrames package. So to get to these instructions, I don't know what I was doing. Okay. So yeah, we installed the latest version of BigFrames. Yeah, for the folks local, make sure you're connected to that PyData NYC. You can see up on the top left what your project choice is. You might have to switch to the Junix org that we use for our test projects. All right. So we've installed BigFrames. We're connected to the right project. Let's start using it. So first things first, we import it. And then we're going to set that partial ordering mode for more efficient queries at the trade-off of maybe a little less drop-in pandas compatibility. And then let's talk about the data that we're going to analyze today. So Google has a cloud public data set program where we've partnered with government agencies around the world, nonprofits, and for-profit companies that want to make their data open and accessible to folks. So in this case, we're using the Consumer Complaint Database, which is collected by the United States Consumer Financial Protection Bureau. They make that data public, and we have some pipelines to pull that data into BigQuery on this table. And for the folks at home, you can click this link. Again, my login's a little screwed up, but learn a little bit more about that public data set. So to use it from BigFrames, BigQuery DataFrames, we're going to call readGBQ, and that looks a lot like it would look like in Pandas GBQ, but instead of downloading that whole table to your local notebook, or in this case to our cloud notebook runtime, we're just creating basically a promise of that table. So this feedback data frame represents that table, but we haven't had to download anything. There's a couple warnings. I'm aware of those. It's on my to-do list to fix them. you can ignore them. It's okay. So one of those APIs that's not compatible with partial ordering mode is head. And that's because head means give me the first whatever rows of the data frame. Since we haven't specified an ordering for this data frame, that head is technically ambiguous. Like the first rows doesn't really mean anything. So instead of head, we provide this API called peak to, instead of the first few rows, just download a arbitrary selection of rows. So that's basically going to generate a select star with a limit clause. So here we've got a selection of rows from a variety of years, and we could see all the different columns as well as, an example of the data that's in there. Yeah, in this case, there's the date the complaint was entered, what kind of financial product or issue the customer might have been having. And then important for later on in the workshop, we actually have the complaint that some person who was having trouble wrote. So they have, some unstructured stories about, what went wrong. Just like pandas, we also provide D-types, and these are emulating pandas types. In this case, we are emulating the arrow D-type because arrow corresponds a little more closely to what BigQuery does semantic-wise. But yeah, you can see this particular table. There isn't really much numeric data. It's all dates, strings, and booleans. But we're still going to be able to do a little bit of structured analysis later on. One thing you might be used to doing in BigQuery DataFrame or in Pandas is calling describe. You can do that same thing in BigQuery DataFrames. So here I've got some code to do describe. But one important thing I'm doing here is I'm actually dropping a few columns. These are those, the actual text of the complaint that the consumer, as well as the response to that consumer. Those are larger columns. They're, quite a bit of text data. So by dropping those and not including them in the describe, we can make our query a little more efficient, so we don't have to read those larger columns. So since there's not numeric data, this is going to give us back a little less information than it would if we were processing integers or floating points. So we get the count, which is the number of non-null values, which isn't necessarily equal to the number of rows. As you can see, the count is a little different for some of these versus others, depending on how many null values we had. And then we have n unique, which is the number of unique values in that column. So you can see a lot of these are more categorical style string columns. So there's only 18 different product types in this data set. But there are the same number of non-null values as there are unique values for complaint ID. So that one, just by taking a look at describe, we can see that some things are repeated quite often and some things are unique values that we could potentially use as a join key if we needed to. So we've got kind of the high-level picture. let's dive in a little bit more and use some of these Pandas-style analytics APIs. So one thing I was curious about, we have a column here which is state. I'm curious how many complaints we get per state. So let's run some queries to figure that out. So here this is all Pandas compatible. We're doing a group by here. And notably, I'm calling as index equals false. You could do that in Pandas too, and it can be really handy sometimes. Without specifying that, Pandas and BigQuery DataFrames as well sets the group by key or keys, if you have more than one, as the index on the output data frame. So in this case, with as index equals false, we're including those group by keys as just a regular column in the output, which is a little easier to deal with, in my opinion. So that's why I'm doing it here. I call size, which will get us, unlike count above, this will give us the actual number of rows in each group, whether there's null values or not. And then rename it to be a little more understandable. And then I mentioned before with head that we don't have an ordering on this data frame. We can still add an ordering. So in this case, we're calling sort values and sorting this data frame by the total number of complaints in descending order. So we'll get the states with the most complaints first in our data frame. And when I run that, just like with readGBQ, that gives us a promise for results. It didn't actually run a query in BigQuery. So to get it to run a query, we need to ask for some data. So here we see we can run head. Unlike before where it failed, this time it succeeded, and that's because we have an order by or sort values in our data frame. And then really important here, we call toPandas. So toPandas is how we convert from a BigQuery data frame into a Pandas data frame. And that will go and run your query and download all the results to your notebook. So if you're calling toPandas, you might either want to set some of the sampling options we provide in toPandas, or just make sure your results will fit on the notebook. And then now that we have a Pandas data frame, we can visualize it however we want. In this case, I'll do a bar chart just so it's easy to see kind of the scale of things. So we can see California receives the most number of complaints in this table. Hard to tell much beyond that other than there's more. The population is also higher in California, so I can't really tell just from looking at this if that's of concern or not. So what we're going to do now is do some joins. So I mentioned population. So the U.S. Census Bureau actually has I think we're getting a question. I don't know. We got a question. Can you call .info? And the answer is yes, but since we are using a partial ordering mode here, we haven't quite implemented that for partial ordering mode. So in this case, we could call info if we explicitly set an index. But for now, we'll skip over that. So we have implemented it, but not in this partial ordering mode that we're using. So yeah, let's figure out the population of these various states and visualize our complaints data in that context. So the U.S. Census Bureau provides some public data, and we've imported that into BigQuery as well through our Cloud Public Data program. And then we also have this geo-US boundaries public data set. And the reason we need to pull in both of these is because the Census Bureau doesn't provide that two-letter state code. So if we take a look here, you can ignore this too. This is a known issue. If you see this too many labels, you just run it again and it should work. We'll get that fixed. But yeah, you can see we had this GeoID column, which corresponds to which state the survey has, and a whole bunch of different populations and other information. But it does not have that two-letter code, so it's going to be difficult for us to join that up with our original data. Yeah, we can take a look at the D types too. There's a lot of columns on this table, but I promise you, one of them is not the state, the two-letter state code. So instead, we need to join it with this geo-US boundaries table, which geo-US boundaries has both GeoID and the two-letter code. And there's that labels issue again, so we'll just rerun that cell. So yeah, here we see GeoID, and those numbers correspond to the same numbers that the Census Bureau use. But as well, it has this state column, which we can use as a join key on the complaints database. One other difference, so the boundaries data, I think, uses a leading 0 on the GeoID, whereas the Census Bureau does not. So since the Census Bureau and the geo boundaries aren't consistent in if they use a leading 0, we're just going to call this pandas compatible pad method to make sure they always have a leading 0, and that way we can do a join. So there's several ways you could do a join in pandas, and likewise there's several ways you could do a join in BigQuery DataFrames. Here I'm calling set index, and if you're not familiar, index in pandas actually gets used as the join key, and that's whether you're doing an explicit join with this dot join, or if you're, say, adding two data frames together, that does an implicit join by that index column or multiple columns if you're using a multi-index. You could also do dot merge and give it a column to use as the key to join on. And that definitely would have worked in this case, but it's just a matter of preference, I suppose. So that joined our two populations together. So now we have the population as well as our state column. So we've got the population with that 2D code. So I'm going to try to visualize that. I'm seeing complaints and pops is not defined. Oh, that's because I missed a step. So we need to do one more join. So we're going to join our complaints with this new populations data frame I created. So this time, instead of joining by GeoID, I'm joining by that two-letter state ID. And now we can visualize it. So I'm calling two pandas. That gets me pandas data frame, and then I'm doing a scatter plot on that. Since we're only dealing with 50-ish rows, calling 2 pandas should be just fine. Yeah, and so we can see here we've got a pretty linear relationship, at least if I eyeball it. But there are a couple of outliers. Just due to time, I'm not going to go into what those outliers are. But I'll leave it as an exercise for you all if you want to do that on your own. I do recommend it. And then also it could be fun to come up with some hypotheses for why those 2 states might be outliers. It puts some example hypotheses there. So yeah, now might be a good chance to ask questions. Okay, so now we're going to process some unstructured data. So if you remember before, we had that complaint narrative column. So we're going to kind of start from the beginning again. So I've got the imports here, as well as kind of resetting that feedback data frame, just making sure we're working from a clean slate. And looking at the shape of this, we can see we're working with about 3.5 million rows. One thing that'll be important going forward is how we specify the filters. So since we're doing ordering mode equals partial, we can do pandas style filters. And those pandas styles filters will actually decrease the amount of rows that you need to read because of that consistent or deterministic ordering and the associated sequential index. If you don't specify that option, these filters will still reduce the number of rows in your data frame, but it wouldn't reduce the number of rows in the actual query that get read. So it's important, if you're not using ordering mode equals partial, to specify those filters at read time instead. So in this case, we're trying to reduce the count to about 150 rows, because we've got a full room here, and we're going to be calling some more advanced models, and those models have limited per project quota. So I was able to increase the quota to be able to handle all of you running in person at the same time. But yeah, if we are using a new project, you might be very limited quota. So, for example, if you're using the free tier, I believe the quota starts at 5 requests to our text embedding model, 5 requests per minute. And so if you are doing this at home, you might want to set or uncomment that line, which will reduce the number of rows to 5. But in this case, about 150 should be good enough for our demo and keep things moving relatively quickly. And feel free to try this, removing some of those filters. Obviously, the more data you process, the more expensive it'll be. So I guess be a little careful with that. Might want to double check with the dot shape how many rows you're going to be feeding to our AI models. But yeah, in this case, we've got 165 rows, which is about right. One other important thing about ordering mode equals partial is drop duplicates currently doesn't work in that mode. And that's because in Pandas, drop duplicates actually is an ordered API. There's a few options to it, but mainly you can say, hey, drop all the duplicates but keep the first row, or drop all the duplicates but keep the last row. And that's not really defined if we don't have a strict ordering over all the rows. So the more like SQL-y way or BigQuery way to get rid of duplicates is to actually do a group by. And then we're calling .size, but we're not really caring about the size per group in this case. We're just using it to coalesce all those duplicates into a single row. So yeah, in this case, we're grabbing that consumer complaint narrative column. And yeah, I did as index equals false above. And so we've got, the complaint narrative column as well as the count, row count. And so we're just selecting that complaint narrative column again. So looking at the counts, we've got 154 rows after our group by. So there were a couple of duplicates, and that might kind of throw off our model a little bit, weight those duplicates a little more than we would like. So we're going to get rid of those. And now, so we've got our text data, which is very much unstructured. We're going to turn that into more structured data. And the way we're going to do that is with what's called a text embedding model. So a text embedding model takes your unstructured data and turns it into structured. In our case, a list of floating point numbers, also known as a vector. So these models, you can take a look at one of Google's research papers. I've linked here, and this is a screenshot of that. This text embedding model is derived from a large language model such as Gemini, and it's used to generate a vector, and that vector is a point in space with very specific properties. It's intended to kind of correspond to the meaning of that text. So you could have two texts, this person is the king, and the king is this person. And those meanings are going to be pretty darn close to each other. So those vectors should appear pretty close in that multi-dimensional vector space. And I definitely recommend taking a look at how that text embedding model is produced and kind of more of the properties associated with it. But in our case, we're using it because similar things should appear close to each other in that high dimensional space. So our job seems to have finished. So we've got embeddings for each of our 154 rows. So let's take a look at those. So just like before, we're going to use peak, .peak on our data frame. And that'll let us take a look at what these vectors look like. So we can see the actual vector here in this ML generate embedding result column, as well as a little bit about what the model found, such as the number of tokens, which kind of corresponds to the number of words, not exactly. And then another really important column here is the embedding status. So one thing about using this model is it might fail for a couple of the rows in your job. And rather than fail the whole query, what we do is we populate this status to say, hey, we couldn't get the embedding for this particular row. That might be for a variety of things. It might be, there was a hiccup in the network somewhere, or it could be some safety filter got flagged where we didn't want to generate the vector for that. What I'm going to do, we could only see like a couple of floating point numbers in that embedding column. Just wanted you to see what this embedding column looks like in full. So what we're going to do there is call peak again, but this time take a look at just that first column, one row from that first column. And you can see there's quite a few floating points. This is a very high dimensional space that we're working with. So that's going to be a bit of a pain to scroll through for the rest of the tutorial. So I recommend clicking on that cell and then the three dots and saying clear output, because we don't really need to look at that. I just wanted to kind of demonstrate just how large those vectors are. Next thing we're going to do is just remove any of the rows that had a failure. So I mentioned that status is going to be filled with something if there was a failure. So we just select all the ones where there's nothing in that status column. In this case, we get 154 rows back, which is the same as the amount we fed into it. So in this case, thankfully, we didn't have any failures. So yeah, now we've got ourselves some numeric data, some more structured data, but it's still kind of meaningless to me as just a mere human looking at that vector. So let's try to make some more sense out of that column. So to do that, we're going to use a more traditional machine learning technique. In this case, a unsupervised learning technique called k-means. So k-means is a clustering algorithm, one of the simpler clustering algorithms, where you actually have to specify the number of clusters ahead of time. So we're going to get that going using our fit again. And then while that goes, I'll give you a little picture of what k-means is. Google publishes a pretty detailed intro to machine learning course online. So this screenshot is from there. And I do recommend you go check that out. But yeah, the way k-means works is we pick, based on the number of clusters you've decided to group the data into, we pick kind of arbitrarily, in this case 5 data points to be the centers of those clusters. And then we go through all the points and say, which cluster is it closest to? And then we find the average position of all of those points. And that'll be the new center. And we repeat that process until the center stops moving. And that's how we know, our clusters are pretty stable. So it's still running. Yep, just finished. The other thing I wanted to mention is I've got a link here. So 5 was kind of arbitrarily chosen. You might want to, depending on your data, pick more or fewer. So I linked to an article with some metrics you can use to determine how good was my clustering, and then use that to choose your number of clusters, kind of optimizing one of those metrics. And then we had a question too. Are we using vertex for this k-means, or are we using something else? In this case, this is a model that's built into BigQuery machine learning. So BigQuery machine learning has the capability of calling out to vertex for some things, as well as some native models built into it. This is one of our native models. So once we've figured out what that fit, what the centroids are, we can call predict and assign our data to particular clusters. In this case, when we called peak, we got a bunch of data from cluster number 1. Who knows what's in cluster number 1? We'll try to figure that out. Going to remove those failures again. In this case, there weren't any embedding failures, so this step isn't really necessary, but we'll give it a go anyway. And then one thing we can figure out is, okay, we've got these clusters. How big are those clusters? So we're just going to do a group by, and then remember dot size will give us the row count per group. And I'm not calling 2 pandas here. I could, and maybe should. But if you try to visualize a BigQuery DataFrames object in your notebook, that's very similar to what 2pandas or peak is doing. It's still going to run the query and try to show you a visualization of that. In this case, we can see we've got our 5 groups, some of them larger, some of them smaller. Our largest group is that number 2 with 69 points in it. And then group 3's got some, who knows what kind of data in it, but there's one that's kind of off on its own. And then, the other groups are, I guess, more medium-sized. This tells us something. There exist clusterings of various sizes. Let's try to understand what's in those clusters. So to do that, we're going to use another one of our more advanced AI models. In this case, the actual LLM. So we're going to use a version of Gemini called Gemini 1.5 Flash. All right, so we're going to try to make some sense out of these clusters. So we're going to use Gemini, actually, so Google's large language model, specifically Gemini 1.5 Flash, which is a smaller model. So it'll be a little cheaper, a little less resource intensive, which is perfect for these data that we're working with, as well as since we have all of you running at once, conserving resources is also handy for that. So we're going to run that LLM. In this case, we're running it once per cluster. We're downloading via peak a sample of 40 rows from each cluster. I guess since we're only working with 150 rows-ish total, some of those clusters we're just downloading the whole thing. And we're doing some prompt engineering here. So we're asking Gemini to summarize. So what is the main concern in this list of user complaints? And then at the very end, after we've kind of pasted in all those complaints, we say, write the main issue using a formal tone. So I don't want it to explain like I'm 5. This is for a report that I might send to my boss. So I'm asking for a formal tone. The other thing to note here is we are setting temperature equals to, so to get those into BigQuery DataFrames, we're calling BPD.DataFrame, just like you would with the Pandas DataFrame constructor. We're specifically selecting that Flash model. And then we're calling predict, which will run our LLM with those prompts, and setting temperature 0 just so we get a more consistent output each time. You might want to play around with that. I forget what the default value is, but here, just for the demo, for consistency, we're setting it to 0. And you can see not too much that we can actually see from this output. Gemini summarized each as the main issue or the main concern, and then it gets cut off by our data frame visualization. So let's try to make a better formatted report. So I could go through, do a for loop, and try to format that myself. I'm being a little lazy today, so let's get Gemini to do it. So in this code, I've got Gemini again, but my prompt this time is turn this list of issues into a short, concise report. So I'm asking for another summary, and then at the very end, I say write a markdown text format report, and that's because we're using this Markdown plugin for Jupyter or IPython or, in our case, Colab, which integrates with that whole ecosystem. So we're going to render some Markdown text that Gemini produces for us. So if we run that, we should get our report out. And since it's just one row, it shouldn't take too long. So yeah, here we go. We've got our headings. So it did do some Markdown formatting for us, as well as some different categories of issue that might come up. So in this case, identity theft, misleading information, predatory lending practices. So this is a small sample of the data. And a couple things to note here. This was an example that was meant to represent, any sort of unstructured data. So you can imagine having a list of warranty claims or consumer reviews for your products, or call center calls, transcripts, really anything. We could use this same technique to try and make some sense of, data that would otherwise be pretty difficult to really use meaningfully. Okay, so I'm getting some questions about cost. So it is a little hard to predict the cost because we've got several APIs we're working with. We've got BigQuery, we've got Gemini, we've got BigQuery Machine Learning. Could throw some remote functions in there too, cloud functions. There's a few things you can do. There is a calculator for Google Cloud to figure out some cost estimates based on your expected workload size. There's also a way to do a dry run. So a dry run, if you set the repr mode, it'll print out a cost estimate. It'll be an upper estimate in terms of the BigQuery costs. I'm hearing some requests to, rather than make that an option, potentially we could provide a method to do a dry run. I think that's a really good feature, and I'll follow up with the team on that. Yeah, I think I'll wrap up here. Thanks everybody for coming. It was awesome to see you all process some structured and unstructured data. I hope that you're able to apply this to the work that you do. And if you have any more questions, I'll be around. Thanks again.